Thunström, I hope I pronounced your name correctly, from Uppsala University, and he's going to talk about electronic entanglement in strongly correlated materials.
So let me try to share the screen.
Yes, it would be great if you could.
Like this, I hope.
Yeah, maybe go to presentation mode and...
Okay, is it visible for you?
Yep, so I think it's time for you.
Good, thank you. So I will talk about electronic entanglement in strongly correlated materials, and this talk is based on this recent article that Anna Galler and me published. So, as an introduction, of course, there are different forms of entanglement for electrons. And what Lexin just talked about is this orbital or mode entanglement, where you define it with respect to orbital partition. And then for pure states, then this reduces to looking at the entropy of the partially reduced density operator. And if you include, like Lexin did, some local restrictions on your Hamiltonian, or even fundamental restrictions like the parity superselection rule, then you have on top of the mode entanglement, you put these restrictions, giving you, for example, this particle number restricted mode entanglement by Weissman. So, and in this mode entanglement, you first measure the local occupation before you measure the orbital entanglement. And this is what the question, the last question was about, that we in this paper also show that after the local occupation measurement, then if the state is NSSR mode entangled, it will also be particle entangled. But it's not the state before the local occupation measurement, but actually the state after it. But in this talk, I will not actually focus on orbital entanglement, although it's important for quantum teleportation of electrons, which we go through in this paper. It's what can I say? In materials, then the Hamiltonian almost always have off-diagonal, or in this sense, non-local terms with respect to your orbital partitions. So for looking at just materials, there is another form of entanglement that we found important, or is important. And this is what's called particle or electronic entanglement. So one should note that this particle entanglement, it's not the same as what Weissman introduced, although they also called it particle entanglement. But instead, this form of entanglement, here you don't do a bipartition. Instead, what you focus on is the quantum correlations of the electrons. And you measure it by looking at the distance to, well, the closest statistical mixture of Fock states, which you then call, the Fock states are then by definition non-entangled states. And in this talk, I will not look at, I will not treat the very difficult question of how to do it with mixed states, but I will focus on the much easier case where you have pure states, and where we measure the distance by using because then you can use the overlap. For mixed states, you could possibly use the fidelity instead. There is another way to measure the particle entanglement when you have pure states, and that is to look at the entropy, in this case the linear entropy, but one can use von Neumann entropy as well. So you look at the entropy of the one particle reduced density matrix, defined like this. So if we now look at the formation of particle entanglement, how do we get particle entanglement? Well, then we need to look at the Hamiltonian. So if we divide our Hamiltonian into one part that contains all one-body interactions, for example, kinetic energy or the effective potential given by the core electrons, which you probably would trace out of this of your system. And then the second term is your Coulomb interaction. And one important thing to note, which also simplifies the issue, is that the Coulomb interaction is a density-density interaction given in real space. So this relates to what Christian talked about, that we should definitely take into account that we have just two-body interactions. But in fact, it's even in some sense simpler than that. We have a two-body interaction of a density-density shape in a known basis. So this will come back later on when we look at the evolution of the system. So, well, the major issue is, though, that the one-body terms and the interaction term, they do not commute. However, we can still consider the evolution of the two terms separately by doing at least a formal Trotter decomposition of the evolution, like this. So when you divide the time steps in infinitely small steps, then you can separate the two. So now I will proceed and look at the one particle unitary evolution operator first, but more use it as a way to introduce what we will look at when we do the two particle unitary operator. So yeah, because the one particle evolution operator, it's very well known what it does. But here I go through it anyway as a pedagogical introduction. So to evaluate this, what you first do is that you diagonalize this one body term, because then you can write the exponent in terms of well, you see that the creation operators are now for the same spin orbital. So this means that all these diagonal terms will commute with each other. There is no ij that would not commute. And since they commute, the terms and exponents, we can Taylor expand it. And after a bit of algebra, you end up with this expression. So where you have then just a long product of well, creation operators. And what this does is that if you have a creation operator coming here, then it will pick up a phase. And if it's an annihilation operator instead, then it will just pass through because of this identity here. So a creation operator in this eigenbasis, so written in the orbital eigenbasis, is therefore transformed as this. If you take the evolution operator, one body evolution operator, and act on the creation operator, well, the creation operator will just pass through and pick up a phase given by the orbital eigenvalue. So if you then take, well, this was in the eigenbasis, but then you can of course rotate into any basis here. And the difference is that then you will sum up, well, you will make a unitary transformation including this phase, which then will go into just the matrix representation of the one-body evolution operator. So this shows that the only thing that happens for a general creation operator that goes through the one-body evolution operator is that it's transformed into another creation operator in another orbital basis. But transforming this transformation, it's a fixed transformation. It only depends, so this matrix is fixed, which means that if you start out with a Fock state, then afterwards, after you have evolved it using this operator, you end up with a Fock state as well, just written in another basis. So what this means is that the particle entanglement is not affected by this one particle evolution operator. But this is not surprising, and it's very well known. So let's go on now to the two-body evolution operator. So now we use that the interaction is diagonal in real space, which means that these terms are also forming this kind of density-density interaction. And this means also that, in fact, these diagonal terms commute with each other. So we can again do the Taylor expansion of V to get a very similar expression as before. It's just that we have more operators here. Now, if we apply a creation operator in the eigenbasis, so in the R, in the real space, like a real space point, then one can show after some algebra that we get a very similar expression as for the one particle, for one body operator. And the exception is that instead of a fixed phase, we now get an operator that depends on the position of the creation operator that passed through the two-body evolution operator. And this operator, well, it looks like this. It's just given the energy or the phase related to, well, having an electron at position R, and then well, summing over all other positions and spins. So what does this do now if we have a Fock space? Well, a Fock state. Well, as V2 pass through the chain of creation operators that define your Fock state, then after each point, it creates a trail of these one particle operators, evolution operators, which then depend on the creation operator it just passed. So now these operators, now if you continue to pull them to the right towards the vacuum, then they will pass through operators, the other creation operators, and leave a trail of phases in turn after them. But these phases now, in comparison to the previous case, now these phases do not only depend on in this case, the R prime, but it also depends on R. Meaning that if you have different Fock states, well, then these phases will be different. So there is not a fixed orbital transformation like in the previous case. So there is no way to absorb all the phases and come back to a single Fock state if you started from one. Well, except if you happen to start from an eigenstate of the interaction. So, as I said, this will affect then the particle entanglement. You will no longer be, the distance to the closest Fock state can absolutely change. And it will also affect mode entanglement, but only if the interaction will be, if you have interaction between your two orbital partitions, A and B. Well, one could perhaps say that this is not such a surprising result, but I find that the formalism becomes quite beautiful with all these trails of the phases. So let's apply this to then a simple toy model. So let's consider the interaction operator here being on a density form for an orbital 1 and only locally on orbital 2. And we consider that we start from an initial state that is clearly a Fock state, but in the orbital basis defined like this. If we take this state and evolve it according to the two-particle evolution operator, then, well, given the formula before, we end up with this state where we have these phases. And as you start out, if t is equal to 0, then, well, then it's only this term, which means that the state is a Fock state and not particle entangled, while at t equal to pi divided by 2u, then we get a maximally particle entangled maximally particle entangled state, and also maximally mode entangled between A and B, because then these two terms have exactly the same weight. So with regards to the mode entanglement, we can see that, yeah, it does change between A and B. But if you look at the mode entanglement between the original orbitals, the orbital 1 and 2, it actually, well, it remains constant, because in this toy model, the interaction is local. So there is the orbital partition 1 does not affect orbital phase.
Patrik, you have 3 more minutes.
Okay, so then we can look at what happens if we introduce a detector. So in an idealized one particle detection of an electron, you would have an initial state, an electron in a free orbital, in a free electron E. You would have the state of the system in some state with a detector in its primed state. And then you would also have a superposition between this and the system where it does not have an electron in the free state. And the final state after the detection would be that the detector would react, it would cascade due to the free electron it picks up. While in this case, if there is no electron there, then it would remain in its primed state. So this detection is, for all practical purposes, irreversible, and these two pointer states of the detectors are orthogonal, which means that you cannot access their relative phases between the pointer states. So this means that the superposition that we have in this final state is actually, for all practical purposes, just a statistical correlation. So therefore, I will now focus instead of the full system, I will focus on the system to look at what happens to the particle entanglement in the system when you do the detection. So in that case, in this way, I project out the detector, and then we get the initial state becomes this, and the final state divides in two different parts. This is what you get if the detector is activated, and this if the detector is still in its primed state. So some algebra, which is part of the appendix on this article, yields that the entanglement in the initial state is always bigger or equal to the entanglement of the states of the system after the detection. So what's written here is then exactly the same as what's written here. So you have that the detection of an electron in a given spin orbital does not increase the particle entanglement in the system on average. And this is a quite useful this is quite useful. So with this, we can look at different experimental detections. So for example, if we have a photo emission experiment, then we send in a photon and we get out an electron, which we then detect. So if we have a high energy photon, this makes the detection very close, the excitation very close to a one-body interaction, or not interaction, a one-body process. So then this means, if we look at the formulas in the previous slide, that the ideal photo emission experiment does not increase the particle entanglement within the system. It of course increases the entanglement between the system and the detector, but not within the system. For an optical experiment, however, where we have a photon in and photon out, in this case, we can get a change in the particle entanglement, because the emission of the photon from the system and the absorption of the photon in the detector goes together. It becomes an interaction. And this means that you can go from an excited Fock state that through this emission of the photon becomes a superposition of two different Fock states. So in a summary, we have looked at orbital and particle entanglement, and this has been simplified greatly by noticing that U is a density-density interaction in real space. And from this, we get quite nice formulas for the different evolution operators, leaving trails of phases as they pass through creation operators. We saw that photo emission does not change the particle entanglement in the system, but an optical measurement can. And as an outlook of this, it would be nice to look at how one would experimentally try to measure the phases between different Fock states, superpositions between Fock states in the system, which was discussed in previously. So thank you very much.
So we thank Patrik for this wonderful overview and with this very nice results. And I think now time is for about some 4 minutes for questions. So please raise hands. And Onur has raised his hand. I don't know who was the first one, but let's start with Onur.
First of all, Patrik, sorry for asking the question to Lex instead of you. Actually, I was not aware of your talk. It is absent in the list of abstract. As far as I remember, in your paper, you also say that we have to consider both type of notions, both particle entanglement and mode entanglement, to capture what happens in real systems. Can you elaborate on this?
So what we say is that well, these different forms of entanglement at least from my point of view, there is not not a competition that one is the true form of entanglement and the other ones are just garbage, you should not consider them. But they are really, they complement each other. So what you get from, when you look at these, what happens in a material and what, so how correlated the electrons are, then this does not really need a bipartition, or putting a bipartition can even be quite artificial. While in teleportation schemes, where you put restrictions on the sets of operators that you want to do, or you put the restriction, you say the Hamiltonian should not have non-local terms. You do not allow for a coherent transport of electrons over the orbital bipartitions. Then in those cases, it makes a lot of sense instead to look at this mode entanglement. And in particular, this NSSR restricted mode entanglement. Well, but we do look at, what can I say, a bit of a special case in the examples we look at, where we look at what happens if you have a shared state between the two orbital partitions A and B, and you want to, what can I say, teleport just half of the state over. And in that case, it really depends on how you do your bipartition, if this NSSR restriction well captures this the success rate of the teleportation scheme.
So I think there's only half a minute left, so maybe it's pretty late in Europe. Of course, in the US it's only afternoon, but maybe I think it's time for thank you for Patrik again, and then I think we all could thank for Christian and David, and also Lexi and Julia and all the others who helped them for this wonderful workshop. And I can see that there are a lot of applauses on the chat window.